So I'll present you Tim Williams from Bloomberg, which will be speaking about some way to write some kind of generic recursion patterns with examples in compilers.
Hello all. My name's Tim Williams from Bloomberg, and there's quite a few of us Bloombergers here this week, so hopefully you've had a chance to meet at least one of us. Today I'm going to talk about one of the many OCaml projects we have at Bloomberg. Although not really much about this project, it's more on an implementation detail really, but the project I work on is essentially a domain-specific language to model bilateral financial contracts. So these are typically derivatives contracts with two counterparties. The language we have is a restricted pure functional language with no recursion. It has a set of primitives and a means of composition, so we build larger contracts from smaller ones. And we target a contractual representation, essentially a tree, not that dissimilar to the one discussed in the famous Composing Contracts paper from 2000. But crucially, we have users, which is not guaranteed when these projects get kicked off. But we do now have many users. We've been going for 10 years. And our users are typically financial engineers. So these are sort of experts within Bloomberg that take term sheets and turn them into, use this DSL to turn them into a representation that the computer can understand. So this talk is about an experience report based on our use of recursion schemes. And the goal for building our compiler using recursion schemes was really to achieve the following: to factor out and share traversal code, to make use of pattern matching, because we like pattern matching, to better communicate and reason about our traversals. This can be hard when it's explicit recursion everywhere. And of course, to easily identify and exploit opportunities for optimization, and I'll talk a bit about that. And of course, use a catalog of theorems to guide us in the above. So use all the knowledge that has been published over the years about this stuff. So let's start with a sample expression type, not that dissimilar to what we have in our code base. This expression has integer constants, free variables, an add operation, and potentially more. This data type is inductively defined, so it has the syntactic fixed point baked in. So the add operator here refers to expression. And this fundamentally limits what we can do with this type. And there's quite a few papers. I think data types a la carte is one that I recall that talk about all the possibilities if this recursion is opened. We can work with this data type, of course, and traditionally fold functions are often created to sort of factor out the traversals. But these typically work by, these are typically higher order functions with a function per constructor. And so parsing and composing many functions around quickly becomes somewhat awkward when you scale up to complex data types with many constructors. So let's define a non-recursive data type. Let's factor out the recursion. Let's make it open. And so that's what we're trying to do here. We'll call it expr node. So now the add operation refers to the parameter r. We tied a recursive not at the type level by defining the expr type. And then we need these term level functions on the right to inject into this type and project out of it. So why are we doing this? Let's remind ourselves of a bit of category theory. So what we want to do is think in terms of F-algebras instead of thinking in terms of folds. An F-algebra is essentially a triple. The end effector, or the F, is expronode. It's a, the category here is the category of the OCaml types. And then we need a carrier type B, and then we have a morphism of B expronode to B. So this is these are the functions that we want to think in terms of. And in fact, the triple expronode, expert, and fixed on the previous slide, defined on the previous slide, is itself an F-algebra, a special one, the initial algebra. So essentially, we are building folds, but another name for a fold, or the category, the naming category theory is a catamorphism. It's a generalization of a fold. For a list, obviously, it's bracketing from the right. For a tree, it's a bottom-up traversal. And in our code base, all our traversals are fundamentally one or more structured forms of catamorphism. And we actually use F-algebra combinators to add more structure. So we're thinking in terms of F-algebras. And so many of these combinations have fancy names, paramorphisms, zygomorphisms, and so on. But they're all, essentially, they are combinations of adding structure to a catamorphism. For top-down traversals, we achieve that by folding to by using a function carrier type, a higher-order carrier type. So let's derive the catamorphism. So we can do that quite nicely with a commuting diagram from category theory. The initial algebra is on the left, although I've flipped the arrow. I flipped the arrow because the homomorphism at the bottom, cataralg, this function I want to derive, and I can derive it by saying, well, to go up the diagram, we'll compose unfix with map cataralg, and then we'll go down the other side with alg. So you can that definition in OCaml is read straight from that diagram. I've used function composition to define it with this operator, and this obviously relies on a structure preserving map, which works as one would expect. So let's have an example. This example is substituting variables. It's a fold, but it's defined in terms of an algebra, and it takes an environment, and when it encounters a variable, it will look in the environment and it'll replace it if it finds it. And then for all other cases, we delegate to fix. And actually, it's often useful to delegate like this. And here's another example that does so, collecting free variables. With this example now, if we find a free variable, we create a singleton set for a set of identifiers. And then all other cases, we delegate to another F-algebra, and this one parameterized by a monoid with union and empty. And now, in our code base, we write things a bit differently. We actually make the algebras the top-level functions themselves, and because normally those are the things that we're thinking in terms of and composing. But here, to sort of more easily relate it, the algebras are defined as internal definitions. So here's an example of an optimization that we did. The hash consing, some of the contracts that our DSL generate have quite a large in-memory representation because it's a mostly first-order representation. And the F-algebras actually give us a nice framework for implementing hash consing. We need to provide only an alternative recursive type and an injection function to do this. The hash table we used by repurposing OCaml's weak hash set. It's only a few lines of code away from being a weak hash map, and we followed that tip from this paper here. So how do we do that? Well, we create this hashconst wrapper type here that lets us store a pre-computed hash and a unique tag, which is sometimes useful. And we build a new expra. This time, instead of just being expra node, we're now stacked on hashconst there as well. And this is the sort of thing that the open recursive types allow you to do. And obviously, there's a little bit of boilerplate. We need to define equality and hashing for our type as well. That's all pretty straightforward. And then we have an OCaml functor here to make to support hashconsing. So there's obviously a create to create a table, and there's a hashcons that will take the table, take a term, and then it will check if the term is in the table. If it is already, it will return that instance and discard the one it's been given. If it's not in the table, then obviously we'll add it and return the instance it was given. So how might this work? Well, here we create a hashcons table at the top level, and then we change the definition of fix and unfix to accommodate the hashconsing. So that's the only change that needs to be made, you know, this optimization is therefore pretty non-invasive. It's pretty a small change. Memoization, this often goes hand in hand with hashconsing. So we're trading space for time here in certain where necessary. And since we restrict recursion to a library of standard combinators, we can therefore define memoizing variants that can be easily swapped in. So here's a memoizing catamorphism. It's built on another function, memorec, which you would implement very, very easily with a hash table. So what are the experiences? So the good is that recursion schemes have helped us structure our traversals and reduce boilerplate. We've been thinking in terms of F-algebras and F-algebra combinators, and this has helped us to compose and combine traversal code. When you're thinking in folds, it can be, it can be hard to fuse the loops, so to speak. The end-of-functor representation, or the open recursion representation of our expert data type, has allowed for specific variants to easily be created, the hashconsing variant, but also for serialization, for example, transforming the tree to a graph. It's helped with that as well. And our developers have welcomed these abstractions, which are more principled than most other boilerplate reduction frameworks. And the runtime performance has been more than satisfactory, so that's really credit to the OCaml compiler there. Some not so good experiences. So our recursion scheme operators like kata memo are not data type generic. So if we had a different expression type, we'd have to define them again. It's not been a huge problem for us, but obviously we could try to use OCaml module functors here to implement each operator only once. Probably a bigger problem is that the memoizing operator, kata memo, does not work in general when you have a higher order carrier type. So it obviously only caches the creation of the closure, and when you run the closure itself, that works top down, that won't be cached. So we had to work around that by creating sort of specific concrete variations of kata memo for particular problems. So that's annoying. But I suspect that some clever OCaml functor stuff might help with that, but we haven't explored that. And yeah, there's a lot more that I could have talked about, but that's the gist. So thank you for listening.
So we have plenty of time for questions. So have you considered generating the base kata memo and other things like that from PPX? Or?
It's something that we'd be interested in exploring. The answer is no, but it sounds like a good idea.
Just out of curiosity, do you ever solve the expression problem? Do you ever have the combination of different languages that you put together?
Well, is this a question about
application at Bloomberg? If you ever want to extend an existing DSL with more operations and at the same time with more constructs in a modular way?
I understand, yes. No, it's not something that we've tried to solve. We're quite lucky in that there's only the internals of our compiler is not something that we need to publish, and we're sort of free to change that. The problems with compatibility that we have are really around the language itself, which is a different beast. Yeah. Thanks.
Hi. It's a bit out of curiosity as well. Did you try to interact it with co-inductive data types? Because for recursion schemes, sometimes we can have things to manipulate with coalgebras like streams, like sequences. I don't know if that could help, because it looks like it's at a nice level of generalities. So I don't know.
No, that's not something we've explored.
Okay. Thank you.
Thanks.